please hit subscribe.
This problem appears at the 2019 Physics Questionnaire of the Qualifying Examinations for Applicants for Japanese Government or MEXT Scholarships for undergraduate students. The answer key and the original questions are linked in the description. Problem 5. A light ray of wavelength lambda traveling through air is incident on a flat thin soap film at an angle theta to the normal, as shown in figure 5. The thickness of the film is d. The path of the light ray is bent toward the normal in the film with the refraction angle phi. We assume that the index of refraction of air is 1 and denote the index of refraction of the film by n. The first question is to find the wavelength of the light ray in the film, and the second question asks the relationship between theta and phi. Here are some relevant concepts to this problem. First is the index of refraction, n, which is always greater than 1. In a vacuum, the speed of light is c, but in another medium, the speed of light decreases. It is c over n, where n is the index of refraction. Furthermore, the relationship between the incident angle and the angle of refraction is given by Snell's law. This says that the index of refraction in the first medium times the sine of the angle incident to the second medium is equal to the index of refraction in the second medium times the sine of the angle of refraction. To find the wavelength of the light ray, we recall the relationship between the speed and the wavelength and the frequency. In this problem, the frequency remains constant. The speed of light changes when it enters the medium, and so will the wavelength. So, if the new speed of light is c prime, the frequency remains the same, and the wavelength that is new is lambda prime, we can have the following. C prime becomes c over n, because as mentioned, the speed of light in the new medium is c over the index of refraction. And therefore, if we manipulate this, we obtain this equation, and this is in terms of Cf and n. Now, C over F is actually the original wavelength, which is lambda here. And therefore, the new wavelength is given by this expression. The relationship between theta and phi can be obtained from Snell's law. Here, the index of refraction in air is assumed to be 1, and therefore n sub 1 is 1. And theta 1 is the angle within normal, and so theta 1 equals theta. For the second medium, the index of refraction is n, as stated in the problem, and the angle of refraction is phi, and so theta 2 is phi. And if we replace these values here, this replaces this replaces this replaces this, and this. We obtain this expression. The third problem goes, if a certain condition is satisfied, constructive interference occurs between the light reflected at C and the light traveling through the path ABC. The condition is expressed using a non-negative integer m. Find this condition. For this problem, let us review the idea of optical path length. The optical path length P is defined as the product of the index of refraction and the distance traveled by the wave in that medium. And constructive interference happens when the difference in optical path lengths in different media is a multiple of the wavelength of the light that is traveling. For this problem, we need to find the constructive interference condition, and we said that that is when the difference in optical path lengths is an integral multiple of the wavelength. So we need to compute the optical path length in air, which is PC, and the optical path length in the soap film, which is ABC. For the optical path length in air, that is just the index of refraction, which is 1, times the distance from P to C. For the optical path length in the soap film, that will be the index of refraction, which is N, times the distance from A to B, plus the index of refraction times the distance from B to C. And we get the difference between these two optical path lengths. And so that will be this minus this. And we must insist that this be an integral multiple of the wavelength lambda. In this case, because there is a reflection at point B, we must add a shift which is 1/2 of the lambda, or 1/2 of the wavelength. This is because when reflecting off a fixed boundary, the wavelength, or rather the wave, becomes out of phase. And the way we make it out of phase is to shift it by 1/2 of its original wavelength. And that is why we add this term here. If there was no reflection, then we would only have this term here. And now, if we substitute this value here into here, and this into here, we obtain this expression. Now, we divide all sides of the equation by n, and this is what we obtain. This condition, which we obtained in the previous slide, is in fact the condition for constructive interference. However, it is not in the choices. Therefore, we want to simplify this further using the geometry of the problem. From the given geometry of the problem, we can see that this right triangle has this side in common, the hypotenuse, with this other right triangle. And we know that this angle here is theta because we see that this is perpendicular to this here, and therefore the angle here is 90 degrees, just as the angle here is 90 degrees. And because this angle of incidence is theta, this remaining angle here is 90 minus theta. And therefore, the angle that is here is theta, because again, this is the normal, and therefore this angle from here to here is 90 degrees. Furthermore, the angle here must be phi, because the angle here is phi. And again, because this is the normal, the angle here is 90 minus phi. This is a right triangle, and therefore the remaining angle here must be 90 minus the angle here, and that gives us phi. And now from these two right triangles, we can see this relationship. This is from trigonometry. Here, we took the hypotenuse, and we noticed that if we use this triangle above, this hypotenuse is equal to this expression. And if we use the triangle below, the same hypotenuse is equal to this expression. And because that is the same length for the triangle above and below, these expressions must be equal. Now, we try to express this length in terms of this, so we obtain this. Furthermore, we know the relationship between theta and phi, that is from problem 5.2. And so we use that relationship. This is the relationship from 5-2. Now, we replace theta, or rather sine of theta, with this, and that is what we did here. And so, we see that this length is equal to this length. And now, we can go back to this condition that we had at the beginning. AB, that length AB is equal to the length from AQ and the length from Q to B. And so we write AB as AQ plus QB. And the rest will be the same here. However, we have now found out that this length AQ is equal to this expression here. And so we replace AQ here with this expression. And conveniently, this expression cancels with this. And so we are left with QB and BC. And now we have found the answer. For the last problem, we need to find an expression of D, which is the thickness of the soap film, that will satisfy the condition of constructive interference. For this problem, we recall our answer to problem 3. This is the condition for constructive interference. Thus, we need to find an expression for BC and QB. First, let us find an expression for BC in terms of the distance D, because this is what we're looking for. Here, we notice that this line segment is actually a reflection of this other line segment along the perpendicular that goes through B, or rather along the normal that goes through B. And that means that the angle here is equal to the angle here. And therefore the angle here is phi. And from trigonometry, we know that the cosine of this angle is equal to this distance, which is D, over the hypotenuse, which is BC. And if we rearrange that, we see that BC is equal to this expression. For QB, we notice that this is actually another part of another right triangle. First, we just need to find this angle or this angle. However, this angle here is easier to find because we already know from problem 3 that this angle here is phi. We also know from the previous slide that this angle here is phi. And because this angle here is 90 degrees, the angle here in this triangle is 90 minus phi, or 90 minus 2 phi. And again, from trigonometry, we can see that this line segment here, the length of this, is equal to the sine of this angle times the hypotenuse, which is BC. And so we get this. We also know from trigonometry that this expression here is equivalent to cosine of 2 pi, or rather 2 phi. And now we have this expression for QB. Here, we just replaced BC with the value here, and that is this and this, and this becomes this. We rewrite the condition for constructive interference, this into this, and then we replace this with this, and this with this. This is what we obtain. We notice that from trigonometry, we know that this expression is equal to the square of cosine phi minus the square of sine phi. And the 1 is carried here. Now, this expression is equal to the square of cosine phi, and thus the numerator becomes this, the denominator this, and we can see a cancellation possible. And now we can move this entire factor, which is 2 cosine of phi, to the other side here. And this is what we obtain.
If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!